Buonasera, buonasera. Grazie di essere venuti qui stasera così numerosi per provare a capire quello che sappiamo e non sappiamo soprattutto sull'universo e forse quello che non potremo mai sapere sull'universo. E a questo proposito c'è un aneddoto, insomma, interessante, curioso, divertente che mi piace spesso raccontare. Nel 1835 il grande filosofo Auguste Comte, padre del positivismo, scrisse una delle sue opere principali, appunto il corso di filosofia positiva, e scrisse, una delle cose che scrisse con una certa sicurezza in questo trattato, che l'umanità non avrebbe mai potuto empiricamente capire di che cosa sono fatte le stelle, qual è la composizione chimica delle stelle, quali sono le loro proprietà fisiche. Perché? Perché noi osserviamo le stelle da lontano, le stelle sono troppo lontane per andare lì e fare effettivamente dei test empirici, e quindi l'unica cosa che possiamo fare è ricevere la luce. Quindi lui diceva: tutto quello che possiamo fare è collezionare la luce, cercare di stabilire la distanza di questi oggetti, quanto sono grandi, insomma, però non sapremo mai di cosa sono fatte. Qualche anno dopo, nel 1859, il fisico tedesco Gustav Kirchhoff si accorge, fa questa scoperta, che si possono, analizzando la luce emessa dai gas incandescenti, si possono identificare delle linee ben precise, a frequenze ben precise, a lunghezze d'onda ben precise della luce emessa, che dipendono univocamente dalla sostanza di cui è fatto il gas. In questo modo addirittura riesce, analizzando la luce proveniente dal Sole, a identificare una serie di elementi contenuti nell'atmosfera del Sole, e quindi spalanca la porta a quella che poi diventa la spettroscopia e la possibilità per gli astronomi di capire effettivamente la composizione delle stelle. Sono passati soltanto 14 anni da quando Comte ha detto non ce la faremo mai, non lo sapremo mai, a quando qualcuno ha capito come farlo. Quindi questa cosa mi piace spesso ricordarla, perché prima di tutto ci dice di usare un po' di cautela, di stare un po' attenti quando mettiamo dei limiti a quello che gli esseri umani e la scienza può capire o non capire. E l'altra ragione per cui mi piace è perché però ci dice anche effettivamente che in ogni momento storico, in ogni periodo storico, c'è effettivamente un confine alle cose che sappiamo, e quindi c'è questa continua lotta fra il nostro ingegno, fra la nostra possibilità di strappare risposte alla natura e quello che la natura ci tiene nascosto in ogni momento storico. Alla fine, insomma, dal 1800 a oggi poi abbiamo capito un sacco di cose. Abbiamo sicuramente capito non solo di cosa sono fatte le stelle, ma anche cosa le tiene accese, qual è la loro storia, e poi abbiamo capito tantissime cose anche proprio sull'universo su grande scala, come è fatto l'universo, quando ha avuto origine, qual è la sua struttura, come si evolve. Insomma, abbiamo veramente messo insieme un corpus di conoscenze sull'universo incredibilmente grande, però indubbiamente anche adesso, come già nel 1835, ci sono cose che non sappiamo e che quindi possiamo provare a divertirci un po' a capire quali siano queste cose e che cosa ci dicono sulla nostra visione dell'universo. E prima di entrare nel vivo con i due relatori di questa sera, John Barrow e Caleb Scharf, che ci diranno, appunto, proveranno a raccontarci un po' delle cose che non sappiamo, una cosa preliminare che volevo lanciare un po' brevemente per introdurli e che mi sembra interessante è che cos'è l'universo, cioè di cosa parliamo quando parliamo di universo, perché questo un po' ha a che fare con i limiti di quello che sappiamo e che non sappiamo. L'universo, il modo comune di riferirci all'universo è tutto quello che esiste. E però noi astronomi, noi cosmologi, quando osserviamo l'universo, appunto lo facciamo raccogliendo la luce, quindi possiamo, la luce e altre forme di radiazione elettromagnetica, quindi possiamo in realtà soltanto guardare direttamente quello che emette luce o che interagisce direttamente con la luce. Tutto il resto è conoscenza indiretta, e oggi sappiamo per esempio che il 95% di tutto quello che c'è nell'universo non emette luce direttamente, non interagisce con la luce, è una forma di materia e di energia oscura che appunto stiamo cercando di capire. Questa è una delle grandi frontiere dell'astrofisica e della cosmologia. Un'altra cosa che sicuramente ci limita è che quando noi guardiamo la luce che ci arriva da lontano, la luce impiega un tempo finito a raggiungerci perché si sposta appunto a velocità finita, e quindi noi non possiamo guardare più in là della distanza che la luce ha percorso dal momento del Big Bang, 13,8 miliardi di anni fa, fino a oggi. Quindi c'è un orizzonte all'universo effettivamente osservabile, quindi lì si arresta un po' la nostra conoscenza empirica. Eppure, come appunto vedremo nelle due conferenze che stiamo per ascoltare, eppure molte ipotesi di frontiera che hanno a che fare col funzionamento fondamentale della realtà e anche col funzionamento dell'universo oggi ipotizzano che non sia tutto qui, che fuori da questo orizzonte dell'universo osservabile ci siano regioni che possono essere anche molto grandi, addirittura in qualche caso si ipotizza che possano esistere tanti universi, un numero incredibilmente grande di universi, addirittura con leggi fisiche che potrebbero variare in ciascuno di questi universi. E questo secondo me, e tra l'altro appunto nell'universo osservabile esistono centinaia di miliardi di galassie, ognuna di queste galassie contiene centinaia di miliardi di stelle, e sappiamo che attorno a una di queste stelle c'è un pianeta che ospita uno strano fenomeno fisico che per il momento riteniamo unico, cioè l'unica evidenza che abbiamo, ovvero la vita qui sulla Terra. E qui secondo me c'è un po' un punto di contatto fra John Barrow, fra gli interessi di John Barrow e di Caleb Scharf, che sono veramente molto entusiasta di vedere condividere questo palco, perché una delle cose che noi abbiamo usato nei secoli passati proprio per capire l'universo è l'idea che non ci siano posizioni speciali nell'universo, che noi sicuramente non occupiamo una posizione speciale, ma che in media la materia sia distribuita in maniera uniforme. Questa è una cosa che si chiama principio cosmologico e che abbiamo usato proprio per cercare di fare un quadro su grande scala dell'universo. Ecco, John Barrow, che è un cosmologo molto famoso, professore all'Università di Cambridge, e si è occupato moltissimo in passato dei limiti della conoscenza, di quello che possiamo sapere o non sapere. Ha scritto anche recentemente dei libri, proprio le 100 cose che non sappiamo che sapete di non sapere sulla scienza, e poi anche su altri campi della conoscenza umana. Ha anche scritto alcuni anni fa un libro che ormai è diventato un classico, molto importante, è stato molto discusso e anche molto controverso, Il principio antropico cosmologico, insieme a Frank Tipler, in cui affrontava questo problema della rilevanza in qualche modo del nostro ruolo come esseri viventi all'interno dell'universo, e di come la relazione tra l'osservatore che osserva le proprietà dell'universo e l'esistenza stessa, appunto la possibilità che l'osservatore esista, siano in qualche modo legate, possano essere in qualche modo legate. Si è occupato molto di questo legame, e oggi questa cosa è tornata alla ribalta, perché appunto se effettivamente esistessero molti universi, allora ragionamenti di questo tipo, cioè qual è la probabilità che delle forme di vita senzienti, cioè in grado effettivamente di osservare l'universo, possano essere presenti in ciascuno di questi universi, è interessante. Quindi c'è un legame tra queste due cose. E Caleb Scharf, che anche lui viene dalla cosmologia, ma adesso si occupa prevalentemente di astrobiologia, ovvero della ricerca della vita nell'universo, è il direttore del centro di astrobiologia alla Columbia University, ha riflettuto di recente, ha anche scritto un libro che si chiama Il complesso di Copernico, ha riflettuto molto su questa questione, ovvero noi non sappiamo effettivamente quanto sia rara la vita nell'universo, perché abbiamo solo un caso da studiare, che è il nostro, e questa cosa di capire quanto la vita possa essere abbondante nell'universo, che è ancora un'altra delle cose che non sappiamo, un'altra delle grandi frontiere dell'astrofisica, ci può permettere effettivamente di gettare un po' di luce sul nostro posto nell'universo, sulla nostra rilevanza, e anche appunto confrontarci con questa questione del principio copernicano che fino ad oggi ci ha guidato così bene nel capire le cose. Quindi alla fine potremmo dire che spingendoci a osservare e a cercare di capire i limiti del nostro universo, in qualche modo stiamo anche cercando di capire qual è il nostro posto nell'universo, quindi finiamo a chiederci anche quali sono i nostri limiti, forse i limiti della nostra conoscenza. Però lascio molto volentieri la parola prima a John Barrow e poi a Caleb Scharf, che ci spiegheranno un po' più in dettaglio questi problemi. Grazie.
Well, thank you for that introduction. My aim this evening is not to tell you about things that we are about to discover or things that we hope to discover, but to show you how there are some questions in cosmology that we don't expect to ever answer. That cosmology is a science which is rather different to many of the areas of physics or human sciences that we're more familiar with. A few years ago, we were reminded by a perhaps infamous American Secretary of State that most things have what we might call known unknowns. So things that we know we don't know about, but we hope we might. And they also have unknown unknowns. So things that might surprise us because we haven't taken them into account. But the bad news is that cosmology also has unknowable unknowns. So things that we're never going to know, even though we might suspect that we know of their existence and of the general possibility of their existence. The picture that we have of the expanding universe today, as we've just heard briefly summarized, is probably familiar to you at some simple level. The universe is expanding. We're not expanding. The Earth isn't expanding. The solar system isn't expanding. Even our Milky Way galaxy isn't expanding. These structures are held together by other forces which are stronger than the effect of the expansion. To find the markers that trace the expansion, you have to go out to the scale of great clusters of hundreds and thousands of galaxies. These are the markers that trace out the expansion of the universe. And the idea of an expanding universe is very suggestive, even alarming, because it suggests that in the past, the universe was increasingly denser and hotter as we track its history back in time, and that a finite time in the past, it appeared to have a beginning, a time when the density was infinite and the temperature was infinite. We don't know whether that beginning was real. About 15 years ago, we discovered something new and exciting about the expansion of the universe. When it had expanded to about 3/4 of its present extent, the expansion changed gear and started to accelerate. So today we're not only in an expanding universe, but an accelerating universe. And this picture shows the unfolding expansion as it opens out into its present state 13.7 billion years after the apparent beginning. And what cosmologists want to try and do is understand why the universe has the structure we see today. Can we explain it in terms of simple beginnings that rely on aspects of physics at very high temperature, perhaps aspects that we can check or discover at CERN? Well, what are the key problems which are different about cosmology? Well, the obvious one is that if you're a scientist, you're used to carrying out experiments, testing theories. You can't experiment on the universe. You have to just take it as it is. But what we do instead of experiment in astronomy is look for correlations. So your theory might predict that if a galaxy is elliptical, it will contain very old stars. Or if it is flattened in shape, it will be rotating. So these predictions of correlations between different properties are what play the role of experiment. Philosophers of science lay great store quite often, and many scientists perhaps lay greater store by Popper's doctrine that science has to be based upon falsification, that you make a prediction and then you carry out an experiment, and if the results don't agree with the prediction, then your theory is ruled out. This philosophy of science is extraordinarily naive, and it doesn't really work in astronomy. Because when you make your observations, you don't know that the observations have been made correctly. So your prediction may have been falsified because something has been done wrong in the experiment. Or more likely, there is some bias in the way that the evidence is gained. If you were trying to create a catalogue of galaxies to understand their relative brightnesses, that catalogue will be biased. It will always contain an overrepresentation of very bright galaxies compared to faint ones, because the faint ones are harder to see and you will miss them. So Popper's philosophy of science doesn't take into account the fact that observations and experimental evidence are biased in ways that you may not understand, and sometimes they're erroneous. In practice, all you can do as an observer or an experimenter is alter the likelihood that a statement, a prediction, is true. You can never falsify it with certainty. You can never verify it with certainty. In cosmology, we only observe the universe as it was in the past, because light takes a very long time to reach us, tens of billions of years from the most distant objects. And also we have to worry, as we'll see, that there are some things in the distant past of the universe that happen which are intrinsically random because they have a quantum mechanical origin. But astronomers and cosmologists make progress because they have a remarkable theory, one that's more powerful than the theory that's to hand in many of the sciences. Einstein's general theory of relativity provides a set of mathematical equations, every solution of which describes an entire universe. And fortunately for us, our universe is really rather simple compared to how it could have been. It's rather symmetrical. It expands in a spherically symmetric fashion. And so rather simple solutions of Einstein's equations allow us to start making some predictions and talking about the past of the universe. I want to mention 7 key problems where the issue of the known and the unknown arises. The first is rather straightforward. It's what philosophers of cosmology would call underdetermination. The fact that to completely describe the astronomical universe, you need more facts and figures than are available observationally. And so you have to make some assumptions which can't be verified by experiment. The favorite description of all the data on offer today, the simplest model perhaps that might do it, is called Lambda CDM, and it has just 6 parameters, 6 quantities that observers want to fit. But there are at least 24 other parameters that they can't yet see, and they have to assume are very, very small, or even 0. So this is a general problem in cosmology, that you can't make all the observations that you would like to make. And some of the observations you make have to be statistical in character. You gather enormous numbers of bits of information by surveying the sky. But then you have a statistical problem. The study of the radiation in the universe, the background radiation discovered 50 years ago in Princeton, New Jersey, is the heat radiation left over from the hot Big Bang beginning. The variation of its temperature around the sky as you look in angle all the way around the celestial sphere contains a wealth of information about the structure of the universe through which it's propagated, and also the processes that created the fluctuations in it close to the Big Bang. But when you do statistical studies, of this radiation, here is a picture of a temperature map of the sky where the variation in the colors from red down to violet are showing regions which are above average temperature and regions which are below. The trouble is, to do a statistical survey, you've got to be able to take a lot of independent pieces of the sky. And when you want pieces that are rather large in angular extent, bigger than about 10 degrees, 20 times the size of the full moon, you're really rather limited. You can't fit many separate regions of that scale into the sky. And so when you look at the output, the statistical analysis of your sky map, what you're looking at here is the average over the whole sky of the variations in color or temperature on that map up here, and here's the angular scale. So here's the size of the full moon, and here are these rather famous results we've seen in the newspapers in recent years, the predictions of the inflationary universe theory in green against the data in red. But down here you see this fan-shaped region. This is the region of uncertainty that's created by cosmic variance, by the fact that there's a limit to how many independent pieces you can fit in to your survey. So you're never going to do better than this fan in nailing down the agreement between the theory and observation on large scales. On small scales, it's not a problem. The second problem, that's a very fundamental and large one, is that the speed of light is finite. Most of the information that we have in astronomy comes from the propagation of light towards us from different sources. They may be X-rays, they may be gamma rays, they may be infrared or optical photons. But they move at the speed of light, and that means that there is a limit to how far we can see in the universe with a perfect telescope. And we call that limit our horizon. And it's about 14 billion light years away. Tomorrow it'll be one light day further away. But the point here is that all of astronomy and cosmology is based upon the study and the gathering of data from within that finite horizon. There's no doubt a lot of universe beyond our horizon, but we haven't seen it, and almost all of it we will never see. So when people talk about questions like, did the universe have a beginning? Is it infinite or is it finite? We can never answer those questions about the entire universe. We can only answer them about the region within our horizon, the so-called visible universe. A next problem that we face, which I've hinted at already in cosmology, is that there are selection effects, as astronomers call them, or biases. Certain types of evidence is more easily obtained than others. So if your telescope is more sensitive to detecting a certain type of radiation, then it will be that type of radiation that you primarily see. And the art of being a good observer in astronomy is being able to understand these biases and being able to analyze your data in ways that can take them into account. Anybody can gather data at the telescope these days, even me. That's not the challenge of being an observer. The challenge is to reduce and analyze the data in a way that takes as many of these biases as you can think of into account. This has turned out to be a bigger and bigger problem in cosmology over the last 30 to 35 years. You see, most of astronomy is based upon observing things that shine in the dark, stars in distant galaxies, the so-called luminous matter in the universe. And as we heard from Amadeo just now, only about 5% of the universe, we now know, is composed of ordinary material of the sort that composes us and the luminous stars. Luminous material is rather biased. Luminous material is telling you about places in the universe where the density became so high that nuclear reactions could ignite and produce luminosity. So when you look out into the dark night sky and you see blips of light, which are the stars, these are the densest places in the local part of our galaxy. But what's in between just didn't become dense enough for the lights to turn on. So the situation that we have is that if you imagine the density is varying in space in this way, some places it's low, some places it's high, there's a threshold above which nuclear reactions would occur and the matter would become luminous. But elsewhere it's not luminous enough, and the average density down here is rather different to the density of these peaks which became luminous. So we have to worry about whether the characteristics of the luminous peaks, the stars and the galaxies, is a good tracer of the distribution of all the mass in the universe. And we know that in a typical galaxy, there is 10 times more material present than can be seen in luminous matter. In clusters of galaxies, it's the same. We also know that our own presence in the universe introduces a little bias, both in space and in time. We wouldn't expect life to exist in a completely typical place in the universe. We couldn't exist in the center of a star. We would have to exist in a place where the building blocks for biological complexity could arrive and have been produced. So we always have to be conscious that our own existence may have some special feature that means that the part of the universe or the time in the universe's history when we're observing is special. The fourth problem we have to worry about is that there are processes in the early stages of the universe which are intrinsically random. This is not randomness of the sort that you get when you throw a dice on the table at the casino. We use the word randomness there because there is information which we cannot determine, or we cannot determine accurately enough. But there is nothing unknowable in principle about it. But quantum processes that occur in the microscopic world and back in the early stages of the universe are intrinsically random. There is no way that I can predict when the next radioactive decay particle is going to be emitted by a radioactive nucleus. It's not that I'm just not able to find that information out. In a real sense, it does not exist until I observe it. And so what can happen in cosmology is this type of quantum indeterminism that we're used to as a property of the microscopic subatomic world. Because of the expansion of the universe, it can be amplified and enormously enlarged in its extent so that it becomes a characteristic of very large-scale features of the universe, like that distribution of radiation temperature that we just looked at. So a big problem that we have because of this in cosmology is when we see a property of the universe, it might be the distribution of galaxies or the fluctuations in the temperature of that primordial radiation, we want to know which of the properties it displays are things we could attribute perhaps to properties at the beginning of the universe, features of the laws of nature themselves, or the constants of physics, or which of them are the results of random outcomes of so-called symmetry-breaking events. So if I balance this object vertically, then in a perfect vacuum, a quantum fluctuation would make it fall in one direction or the other. The direction it falls is intrinsically random, but it could fall in any direction with equal probability. But if that fall were to determine something about the large-scale structure of the universe, there would be no other explanation for it other than as that random outcome. The biggest impact on cosmological thinking since the 1980s, where this problem has become a large one, is the theory of so-called eternal inflation. The inflationary universe is able to explain a lot of the mysterious features of our universe. Why it expands at the same rate in every direction, why it expands at a very particular rate, and also why those fluctuations exist in the temperature distribution of radiation. So it's a theory we take very seriously. It has very good observational evidence in its favor, and it's overcome a number of possibilities and observations which could have ruled it out completely. But it has a more philosophical aspect to it. The standard picture imagines that there is some tiny patch of space in the early stages of the universe which, for a short, finite period of time, surges in expansion and accelerates dramatically. The elementary particles that do that then decay away, and the normal, decelerating, slower expansion is then resumed and continues until the universe is 3/4 of its present extent. But people then realize, well, it's all very well picking on that tiny region and saying, well, that inflates and expands the little piece of space that's going to become the whole of our visible universe. But what about the other pieces of space beyond its boundary in those early times? They will expand as well and surge by different amounts. And so we predict today that if we could see beyond that visible horizon, where our perfect telescopes can see no further, if we could see beyond that horizon, eventually we would predict that the universe should be very different in structure, different in density and temperature and expansion. And in some variants of this theory, there can even be rather fundamental differences in physics itself in these regions. Each of them inherit entirely the characteristics of these disjoint patches of the universe at some very, very early time. So this is the first time there has been a positive expectation that if you go far enough in the universe, you should eventually find it to become completely different in structure to what it is inside our visible horizon. Soon afterwards, people realized that this new picture that made the geography of the universe much more complicated than you thought also had horrible consequences for the history of the universe. Because each one of these little rapidly inflating regions would produce within itself little parts of itself which themselves would accelerate and inflate. And they in turn would produce subregions which would accelerate and inflate. This was a self-reproducing, eternal process to the future. And we will be sitting inside one of these regions. We don't know what the past was of our region, and we don't really know the future. But we are part of a self-reproducing multiverse, as it's been called. The question, did the universe have a beginning, now has a more complicated answer. our visible part of the universe had a beginning in one of these quantum-induced surges. But the whole multiverse need not have a beginning. It may have had a beginning, we don't know, and almost certainly it's impossible for us ever to tell. So this produces a complexification in time to go with the complexification in space. The fifth of these problems, this multiverse possibility, creates an awkward interpretational problem, because each of those regions that are produced in the multiverse is expected to have rather different properties with regard to fundamental physics. So it's as though you have lots of valleys here, and in one region you will roll into this valley, this region you'll roll into that valley. But each valley defines a different form of the laws of physics, of fundamental particle physics. And so we then begin to see that trying to decide which of these regions we might be residing in is not just a matter of probability, but if one of those regions didn't allow atoms and molecules and life to exist, we couldn't exist in it no matter how probable it was that the universe produced regions of that sort. So this gives rise to a problem which in cosmology is known by a technical term, the measure problem. And it's simply the problem that we don't actually know how to work out the probability of anything in cosmology. We don't know how to work out the probability that the universe ends up in a situation where it's inflated by a particular amount. We don't know how to work out the probability that the laws of physics in each of those different regions of the eternal inflationary universe should have particular properties. This is not just because we're not very good at doing the right calculations, but because we encounter rather fundamental mathematical problems. These universes are infinite in number and infinite in extent. Every time you try to compute an infinity, you get an answer which looks like infinity over infinity. You've run into the same problem that Cantor encountered in the 19th century in trying to define infinities. That the way in which you count the objects in your universe determines the answer you will get for the probabilities. So far, no one really has a good way to work out the probability of life, say, arising, or accelerated expansion arising in any of those regions in the multiverse. Maybe one day there will be some answers of that sort. When there are, you have a very difficult interpretational problem. So suppose that you could do this calculation, and there was one type of universe that was overwhelmingly the most probable outcome of this self-reproduction process. Should we regard that as a prediction of this theory, and also perhaps a prediction that this is the most likely universe that we should observe? Almost certainly not. Because suppose the predictions of the probabilities look like this, so the most probable would sit here, and we might be comparing the value of some property, some constant of nature, some feature of the universe. But if we then said, well, what value would that feature have to take in order for there to be life in the universe, really of any sort that we understand? Say for the atoms of any sort to exist. And we might find that that would confine us to this very narrow region down here that's much less probable. But we would have to exist in a universe that was in this low probability region. We couldn't be here because there are no observers in that region. So you see that in understanding and using the predictions of theories like this, you've got to be able to understand all the ways in which features of the universe affect the evolution and existence and persistence of life, because you have to fold them in to the predictions. Okay, lastly, problem we mentioned at the beginning, we've discovered 15 years ago our universe is accelerating. The Nobel Prize in Physics was given a couple of years ago for this discovery. New methods were devised to enable astronomers to see further than ever before in a way that would allow you to work out how far away were the things that you were seeing. And this is the picture of the expanding universe in time that one now has. The universe inflated back down here in a tiny first early moment, and then it decelerates, but then changes gear when it's about 3/4 of its present extent. And then we are here today during this accelerating phase. This acceleration is a rather unusual and dramatic prediction. It means that in the far, far, far future of the universe, eventually all types of complexity and information processing, and presumably life, will eventually be washed out. The universe will expand too rapidly for new stars and galaxies to form. But there is a final and most unusual consequence of this, and it's connected, I think, to what Caleb will talk about next in black holes. We're used to the idea that if you're inside a black hole, you cannot see out. Information cannot get from inside a black hole to the outside. It would have to go faster than the speed of light in order to do so. This is a consequence of very strong gravitational fields. Einstein taught us that very strong gravitational fields are at root indistinguishable and equivalent to very strong accelerations. In a universe that is accelerating, a horizon of a new sort also eventually will form. And the universe for us will become as though we are living inside a black hole. There will be a fundamental fixed limit to how far we can see into space. And that fixed limit is rather alarming, because gradually, over billions of years, all the stars and eventually all the galaxies that we see composing the expanding universe will pass out through that fixed limit. And if there are astronomers in that far, far future, they will know nothing about the world of outside galaxies that we see. They will know nothing about the expansion of the universe. They will be confined inside a black hole-like region, only able to observe local events. They will not be able to observe the sources of energy in the universe which are creating the acceleration. So for them, cosmology becomes the study of books and journals of what people did in the Golden Age in the past. There they'll learn about things like clusters of galaxies and gravitational lensing and the expansion of the universe and the microwave background radiation, which will no longer be able to penetrate their galaxy because the frequency will become equal to the plasma frequency. So none of these things will be on view to the astronomers of the future. And so here's a little onion skin summary of our knowledge and our ignorance. You might imagine this is a little part of the universe that we have seen so far. It's pretty big. It's 13 or more billion light years in size. If we had a perfect telescope, that's a little bit bigger that we could eventually see today. But in the far, far future, there is a fundamental limit to how far we can see, caused by the acceleration. And beyond that, there is a potentially infinite universe of space and complexity that we can never know of and we can never see. And that in turn, we've seen suggested by our inflationary universe theories, will be part of a larger multiverse of never-ending self-reproduction of universes that may be similar, they may be different. So this is a sombering, long-range scenario. We may be living not only at an epoch in cosmic history that's rather propitious for the production of complex life and carbon, but it might be actually a rather good epoch to be in if you want to study the universe and maximize your knowledge about it as well, because in the future, things will not be like that eventually. Thank you.
Grazie a John Barrow e passiamo al prossimo speaker, Caleb Scharf.
Thank you very much. John, you're a hard act to follow. I feel that everything has been said. So from the sublime to the ridiculous, I'm going to talk about things on a somewhat smaller scale and a somewhat more parochial scale. I'm going to talk about two phenomena that are in many respects entirely different, very, very different from each other, yet share certain things, certain characteristics as pieces of the universe that are actually incredibly important to us. Let me begin the first one, and to do this, I really have to give you a 2-minute introduction to relativity. So in 2 minutes, you'll know all you need to know about relativity. You'll see. Let's talk about space and time. Back at the beginning of the 20th century, Einstein worked to understand the implications of a fact that is very strange, which is that the speed of light in free space is always a constant. It does not depend on the source of the light. It does not depend on the relative motion of someone trying to measure the speed of the light. The speed of light is a universal constant. He realized that a consequence of this is that measurements of length, distance, or intervals of time are not fixed. They are variable things. Space and time are variable things depending on your frame of reference, depending on the motion that you have relative to something that you're trying to measure, and so on. And this is a profoundly disturbing idea. It still is a profoundly disturbing idea, even now, more than 100 years later. And one of the things that Einstein worked very hard at in the years after his initial work on this, his initial work on what is called special relativity, was to try to make other pieces of physics fit into this new picture of the universe. And one of the things he worked on was the notion of gravity. Now, Newton left us with a picture of gravity which says, well, gravity is a force, some kind of mysterious force that happens between objects that have this property we call mass. And that force depends on the separation of objects that has mass. But Einstein has just said that things like the measurements of distances or separations are all relative. So how does nature figure out what the actual force is acting between two objects with mass? Well, Einstein thought about this for many years, and other people were thinking about this too. And to summarize a great deal of work very simplistically, what Einstein said was, well, actually, gravity is a consequence of something else. It's a consequence of a property of space and time, or space-time, which is that mass distorts or warps the fundamental geometry of space-time around it. Think of space-time as a kind of fabric. And space-time is very stiff, but it is flexible. So if you have a lot of mass concentrated together, you can distort it. And when you try to move around in this distorted space-time, this distorted geometry, it's different than moving around in empty space. And that difference is gravity. Now, many people were working with the mathematical framework that was developed to describe the distortion of space-time, this theory of general relativity. And it was quickly realized that if you could concentrate mass enough, if you could make an object so compact and put all of its mass in a very tiny, tiny volume, you would put enormous stress on space-time, so much so that in certain cases you could create a region of distorted space from within which nothing could escape. John already referred to this concept of black holes, although it took a long time for that name to come along. Within this region, nothing can escape, not even light. And the surface of this region has come to be known as the event horizon, because an external observer cannot see anything happening within that surface, and that surface itself is very strange. If you took a clock and put it at that surface, you would see it slow down to a halt at the surface, at the event horizon. Now, this is a very strange concept, and it began purely as a mathematical curiosity, a consequence of looking at the equations for the distortion of space and time for something like a planet or a star, a sphere of mass. And I'll just show you a little movie because it's fun, and it's late at night, so it's good to watch a movie. I'm going to show you a computer animation. This backdrop, it could be anything. This is just a useful picture. In this case, it's a picture of the Milky Way galaxy. It could be Mickey Mouse. It doesn't matter. It's a journey into a very simple black hole. And it's really just to give you a sense of the extraordinary distortion of space and time around such an object. So we'll set it going. We're falling towards the black hole. You can see the image behind is hugely distorted. That's because rays of light coming from behind this object are being bent and curved and lensed. There's a red grid. That is not natural. That may not translate into a good joke. The red grid is simply to illustrate that you can't hide on the far side of a black hole. If you stand on the other side of a black hole, the light from you will be curved around the event horizon and you will see it. So that's an important thing. If you ever find yourself trying to hide behind a black hole, it won't work. Black holes are very extraordinary concepts. And for a long time, it wasn't clear that the universe could make such things. There were a lot of arguments about how could matter become sufficiently concentrated, sufficiently dense. Just to put it in perspective, if I wanted to make a black hole out of the Earth, the planet Earth, I would have to squash the planet Earth down to, well, really the size of the cap on the end of this bottle. At that point, I would create the event horizon about that size, the entire mass of the Earth. The interesting thing is that since the turn of the 20th century, we now know that black holes really do exist. Nature does make these objects. In our galaxy, the Milky Way, we know that there are at least a few thousand, if not tens of thousands, of relatively small ones, meaning objects containing about 10 times the mass of our sun, the product of large stars that burnt through their nuclear fuel and collapsed. But perhaps the best evidence of all comes from something we really didn't expect, which is black holes that we call supermassive. These are black holes that contain millions to billions of times the mass of our sun. And most of them, if not all of them, exist at the center of most galaxies in the universe. Let me show you. What you'll see in the next few seconds is a time-lapse movie. A movie of the motion of stars at the center of the Milky Way galaxy. So each dot here represents a real star over a period of about 10 years. So I'll start that. It zooms in a little bit as well. You can see the stars moving around, swarming around. Let's take a look at the very center. If we watch some of these stars, like that one, it's orbiting around something It's orbiting around something very fast. At the fastest point in that orbit, the star is moving at about 5,000 kilometers a second. That tells us there is an enormous mass that we can't really see in the middle there. In fact, that mass is about 4.3 million times the mass of our sun, compacted into a region smaller than our solar system. It has to be a black hole. There are other ways we can see supermassive black holes. In fact, we can see them across the observable universe, what John called the visible universe, the universe from which light has had time to reach us in the last 13.7 billion years. We can see the presence of supermassive black holes in the center of almost all galaxies back through cosmic time. And we can see them because when matter falls towards black holes, it produces energy. And it produces energy that can flood back out into the universe because it is produced before it reaches that event horizon, before it reaches the point of no return. This is just an artist's impression and animation. As matter falls towards a black hole, and black holes have some other interesting properties, although only a few, one of which is to spin. Matter falling into a spinning black hole is accelerated, it's heated, it crashes into itself. It's like the gurgling of water when you let the water out of the bathtub, at least in my household. It generates heat. The motion of the material is converted into thermal energy, converted into electromagnetic radiation, light. It also, in some cases, around a spinning black hole, can produce jets or streams of particles that actually blast back out into the universe, all because it happens before reaching the event horizon. In fact, it turns out that black holes can be the most efficient converters of matter into energy in the universe. This is really quite surprising. Some of us have a picture of black holes as the end. They're black holes. Nothing escapes. Well, once you get to the event horizon, that's true. But before you get there, enormous amounts of energy can be produced. A black hole can produce energy 50 times more efficiently than nuclear fusion. And that's why you can see these things across the universe. Now I'm going to show you some real images of this. This is a Hubble Space Telescope picture of a galaxy called Cygnus A. It's about 600 million light years from us. This image shows stars and gas and dust, and is about 10,000 light years across. It contains at the center a supermassive black hole that is about 1 billion times the mass of our sun. Now, these are a lot of big numbers. That black hole is consuming matter and generating energy, and we can see that. Let me show you. Let me put it in perspective, the sheer amount of energy. Let's shrink this down and put up another image, a real image of what the black hole is doing. This is a structure seen using a radio telescope made by electrons. Electrons that have been accelerated to close to the speed of light around the black hole and shot out into the universe. This entire image spans 500,000 light years. The black hole, although it's very massive, is tiny on this scale. It's no bigger than our solar system. It's as if a bacterium on my hand suddenly took control of Rome. It's a similar sort of scale. It's an incredible energy output. Let me show you another example. This is a galaxy called Perseus A. It's about 240 million light years from us. It too has a supermassive black hole in the center that is consuming matter and generating energy. In this case, that energy is going into hot gas that surrounds this galaxy. And I'm going to show you an image of that. It's quite extraordinary. This is a real image. It's a real image made using an X-ray telescope. It's looking at gas that is about 10 million degrees 10 million degrees Celsius. But you can see all this structure. You can see these holes, these gaps. You can see ripples in the gas. It's as if someone threw a stone into a lake. That's the result of the black hole, pumping out energy. These ripples are actually sound waves, except the frequency is 57 octaves below that of human hearing. The amount of energy is enormous. 1 trillion watts is being pumped out across this volume of space, across 1 million light years of space. So if you want a really good music system, you have to have a black hole. What we have learned is that this fundamentally alters the nature of galaxies. This energy actually influences how well galaxies can make new stars. It inhibits galaxies from making new stars because it keeps things hot. And to make stars, you have to cool. First, you have to cool gas down so that it condenses into stars. In fact, across the universe, we see this characteristic. These are just some beautiful Hubble Space Telescope images of real galaxies, really just for the pleasure of looking at them. In all such objects, where we find at the center a supermassive black hole, which is microscopic on these scales, we find something very interesting. We find that in many, many cases, the number of stars, the billions, tens of billions of stars in these galaxies, is directly related to the mass of the black hole at the center. Why? I don't know. In fact, although we've seen that this is something critically important, and we've seen that these extraordinary objects, black holes, have a profound effect on entire galaxies, we still don't understand the details. We don't understand exactly what ties the mass of these supermassive black holes to the masses of entire galaxies, to the number of stars in galaxies. We also see these supermassive black holes way back in cosmic time. We don't know how they get there. We have ideas, but we don't know for sure how the universe can make such objects so early with the birth of galaxies. What's the implication for all of it, for the number of stars in the universe, for the number of planets in the universe, for us? We still don't know, and this is a big unknown. Now, let me move to something different but related. Because in some ways it's related through this observation that the number of stars in the observable universe is at some level determined by the activity of black holes. We can see roughly 1 billion trillion stars in the observable universe, in the universe from which light has had time to reach us in the last 13.7 billion years. But right now, we don't know if there's life around any of those other stars. And that's quite a problem. And it's a very interesting problem because at some level it relates to something that we've been thinking about for a long time, since Copernicus and Galileo. This idea that we are not central, a principle of cosmic mediocrity that has been incredibly important for science. But it does say that, well, at least superficially, the circumstances of the Earth, life on Earth, are not special, can't be special, shouldn't be special. Which implies that, well, perhaps life should be everywhere. But we don't know. This is really taking us to a frontier in science. Because the interesting thing is that until 20 years ago, we didn't even know whether any other stars had planets around them. We certainly expected other stars to have planets, but we did not know for sure. That has changed. In fact, in the last 20 years, we've gone from not knowing about any other planets around other stars to having over 4,000 candidate planets, at least 1,000 of which we are pretty confident are real, and the rest are we're fairly sure are real too. We've done this because of a number of extraordinary technological advances. One example is NASA's Kepler Space Telescope that has for a number of years monitored the light coming from 150,000 stars in our Milky Way galaxy, looking for tiny variations due to the presence of planets. We're very confident about what we're seeing, so much so that when a headline like this appears, far-off planets like the Earth dot the galaxy. For once, you should actually believe this headline. We now know that the universe makes planets in great abundance. Planets are made very efficiently. We know that there should be hundreds of billions of planets in our own galaxy, the Milky Way. Planets easily outnumber stars. The statistics are so good that we can begin to make statements like this. We can say with statistical confidence, high statistical confidence, that within 20 light years of the Sun, and that's a mere, it will have to be in miles, 120 trillion miles, so it's our cosmic neighborhood. There should be at least one candidate Earth-like planet, a planet about the same size as the Earth, orbiting a similar star, with the possibility of surface conditions similar to those of the Earth. And that also means that within the Milky Way galaxy, there are at least 15 billion such worlds. Now, on the face of it, this is supportive of the notion of cosmic mediocrity. Suddenly we know that planets are very abundant. Planets, at least for now, are a good first place to think about for life. It's an environment that we know life has occurred on at least once here. But it's not so simple. Because what we've also found is that planets are incredibly diverse, unbelievably diverse. Let me just put up this is just a cross-section of some of the diverse characteristics of planets that we've discovered. I won't go through all of them. There are things like hot Jupiters, gas giant planets that orbit their parent star extremely closely. There are planets that have 2 suns, just like in science fiction. There are super-Earths. These are planets a little bit bigger than the Earth, but not as big as Neptune. They are very numerous. They may represent a majority of planetary types, but such a planet does not exist in the solar system. We have never seen such things before. There are planets that are ocean worlds, covered in oceans that are hundreds of kilometers deep. There are planets that are carbon-rich, where the fundamental geophysics revolves around carbon compounds and not silicate compounds. We're just beginning to scratch the surface. What this diversity means is that really for the first time ever, we can ask the question of where does our solar system stand? How does it compare to these other systems? We've never been able to ask that before. Is the solar system typical? Is it mediocre? Well, we can look at the architecture of the orbits. We can look at the types of planets in our solar system. We can look at the type of star that we orbit. And we can look at the history of our planetary system. And what we find is that, well, yes and no, and it's somewhat unusual. Our solar system is perhaps a 1 in 100 type place. It's somewhat unusual. It's not incredibly unusual, but it is somewhat unusual. Now, when you see something like this, and if you're interested in the question of life in the universe, you have to stop and ask, is there a connection? Is there a connection between this degree of unusualness and the existence of life here? Well, the answer is we don't know. But it's a really interesting question. One of the reasons we don't know is that we don't yet understand either the nature of the origin of life here or its true relationship to this planet, and by extrapolation to the solar system as a whole. We don't know if that unusualness of the solar system is actually critical for life to exist here. But here too, perhaps we're making progress. I'll very briefly show you one interesting example of this. Because if we look at the history of the Earth over the last 4 billion years, what we find is that the environment of the Earth, the surface environment, the chemistry, the temperature, the climate state, is intimately linked to the presence of life. And in particular, it's intimately linked to microbial life, single-celled organisms, bacteria and archaea, the two great branches of single-celled organisms that have been around since ever, have been around for most of the last 4 billion years. These organisms constantly shape and reshape the environment around them. And one of the primary ways in which this happens is through the process of metabolism. Now, metabolism is just the extraction of energy and raw ingredients from your surroundings as a biological entity. And this is your crash course in molecular biology. What is very interesting is that on Earth, there are about 10 primary metabolic pathways, 10 primary ways in which life does this, extracts energy from its environment and raw ingredients. So, for example, we are oxygen respirators. That's a type of metabolism. Another one you might be familiar with is fermentation. Nobody's laughing at that? If we look at the genetic instructions that life uses to build the molecular machines that carry out metabolism, the molecular machines that perform fermentation or help perform oxygen respiration, what we find is it's actually a fairly small number of genes, sequences of genetic code that describe that machinery, about 1,500 genes altogether. And those 1,500 genes are widely dispersed amongst the microbes. Now, the microbes outnumber everything else on the planet. In fact, they are the dominant form of life on Earth, and they always have been. There are trillions upon trillions of them. The interesting thing about that dispersal is that we see that these genes are highly preserved or conserved through time. They don't change much over millions or billions of years. And they're everywhere. They're all over the place in microbes. So much so that if you brought an asteroid in and wiped out 99.9% of life on the planet, it's okay. Well, it's not okay to us. But it's okay for life as a whole because it will not have to reinvent the wheel, because somewhere those key pieces of genetic code describing metabolism will be preserved. Now, that's quite a lot to take in. Some of us are calling this the core planetary gene set. It's kind of the fundamental thing that describes much of life on the Earth. And it's very resilient. In fact, and I'm almost finished here, it's suggestive of a universal mechanism, a way for life to survive for billions of years, irrespective of the details of biochemistry, it will have to do something like this. How else do you survive for billions of years on a planet where there are asteroids coming in, or exploding stars, or other things going wrong all the time? And that's interesting because it's a clue, perhaps, to the connection between a planetary environment and the nature of life and the survival of life. But a big unknown, and I actually think one of the frontiers in this work right now. And it was interesting, earlier in this afternoon, Bruce Lieberman talked about chance in evolution. Well, even if this is a universal mechanism for life that we're beginning to see the clues of, it doesn't tell us how diverse or how different life could be in different circumstances. What if we wound the clock back on the Earth 4 billion years and let it go again? What would happen? Would we have the same organisms? Probably not. How different could it be? And that's very important because at some level we want to understand, are there other things like us? Never mind bacteria, but like us. We're very egocentric. We don't know. It's a big frontier, this idea of randomness in planets, diversity in planets, randomness in evolution, diversity in evolution. It's going to be interesting. So how do I wrap this up? Well, both black holes and life in the universe are two big, interesting, ridiculous phenomena. But we can try to understand them better because we can explore the universe. We can look at the universe. And that's one of the beautiful things. In the case of life in the universe, we're already working very hard at this. We have robotic avatars on Mars looking for the environments that could give rise to life. We're looking at very alien environments in our own solar system. Places like the icy moons Europa or Enceladus, where we think there may be giant oceans beneath the surface that could perhaps incubate life. And we're trying to learn how to look for the signatures of life on distant planets around other stars, looking for the chemical imprint, looking for signs of the core planetary gene set of alien worlds. We are also still thinking about the quest for intelligent technological life, the search for extraterrestrial intelligence, or SETI. It has not gone away. And interestingly, it still remains the search that, although very risky, because you might not find anything, if you did, you would solve two problems at once. You would know that there is life out there, and you would know that some of it is recognizably intelligent. So I will end here by just saying we live in a very special time because we live in a time, and John talked about this in the grand cosmological frame, where we can interrogate the universe. At least we think we can. It's important to be aware that we may be deluding ourselves, but at least for some of these questions, we live at a time where our technology and our brains have got to a point where we can ask these questions. And that, it's looking at a lot of unknowns, but it's truly, truly wonderful. And I'll stop there. Thank you very much.
Grazie Caleb. Devo dire, non solo sono stati estremamente interessanti entrambi i talk, ma anche molto precisi nel rispettare i tempi, quindi penso che abbiamo un po' di tempo per qualche domanda. Laggiù.
Buonasera. La domanda è rivolta soprattutto al professor Barrow. Anche questa sera ci avete ricordato come da Einstein in poi il tempo è è relativo a che cosa? Sostanzialmente mi sembra di capire dal sistema di riferimento e dai campi gravitazionali. Ora mi chiedo, quando anche questa sera abbiamo parlato del tempo dell'universo in tutto il suo insieme, l'orologio di cui ci serviamo per fare riferimento a questo tempo, dove è situato?
What time? Yes. Okay. Yes, when cosmologists, astronomers say that the universe is, say, 14 billion years old, what they mean is the time that would be registered by a clock that was taking part in the expansion of the universe. So if you had someone in a rocket ship with another clock going close to the speed of light in a different direction or orbiting round in a circle, you might be able to extend this time in accord with relativity. But this time that follows the expansion of the universe is called co-moving proper time. So it's a clock that shares the motion of an observer that's expanding isotropically with the universe.
Tutto quanto abbiamo avuto il piacere di ascoltare riguarda l'universo fisico. Ora, qual è cioè in che modo si pone, qual è il rapporto che viene ad avere la coscienza? Ecco, il ruolo della immaterialità, pensiero, cioè coscienza in quanto realtà immateriale. Noi abbiamo parlato di una realtà materiale, l'universo materiale, buchi neri, stelle, eccetera, eccetera. Ma esiste una realtà altrettanto presente perché il nostro pensiero, la nostra coscienza, che abbraccia l'universo, e questo è il grande interrogativo, la nostra coscienza che comprende tutto ciò che voi avete detto. Grazie.
Well, that's too hard a problem for astronomers. We don't know how consciousness has arose in our own species on Earth. I mean, all we can say rather weakly is we might believe that consciousness is something that emerges when a brain reaches a particular level of complexity. And it may be in the future that computer scientists will be able to create artificial brains, computers of sufficient complexity to be able to shed some light on how complicated and unusual could be the emergent collective processes that happen. But astronomers are a long, long way from being able to understand how likely it is that consciousness arises on one of the planets that Caleb has been describing. We're looking at microbial life, very simple forms of life that I believe will be fantastically common all over the universe. But complex, conscious life, like ourselves, we may well find that we are a very, very uncommon example. And to become conscious requires a life form to exist for a very, very long time. And that's a hard thing to do in our universe. We know that advanced civilizations are not signaling to us in ways that Enrico Fermi thought was very puzzling indeed. Maybe they don't live very long because they wipe themselves out by creating nuclear bombs or polluting their environment or overpopulating their planet. It's very easy for us to see why life even on Earth, might not continue very long into the future. But I think external forces, impacts from comets and asteroids, are much more likely to eliminate complex life and send it back to becoming simple life periodically. So it's hard to survive a long time. And so it may be that the time you need to develop complexity at a level needed for consciousness is very hard to achieve.
Yeah, perhaps I could just add to that. I think I agree with John. I think that it's not clear that great biological complexity, consciousness, or intelligence is a positive evolutionary trait. It's not clear that that's a good thing. It may only have happened once here on the Earth. And I think I'm actually more optimistic.
Scusi, no, guardi, facciamo parlare anche... Innanzitutto stava finendo di parlare, quindi non interrompa, primo. Secondo, facciamo parlare anche qualcun altro, perché insomma non è che ci abbiamo tutta la sera.
Yes, I think it's an interesting idea that we tend to think of consciousness as being some type of summit of human achievement. But it may just be a passing phase in evolution. After all, some of the most complicated things that we do, we don't use, are not conscious actions. When you cross the road, you are carrying out millions of complicated mechanical, dynamical calculations about oncoming traffic, what speed should you move at to miss the traffic, what direction should you move in. If I throw a tennis ball at you, you will catch it, but you will not carry out a conscious series of computations about its trajectory. So the deep and ancient abilities that our minds have are not conscious. They're part of the automatic pilot. And we can imagine very advanced beings where everything that we prize in mathematics and physics and science is also conducted on automatic pilot. So you can solve Schrödinger's equation and understand the nature of matter not by consciously calculating, but just intuitively knowing, because your evolutionary history has required you to develop that instant intuition. And consciousness, therefore, would have been something of a phase. It's not particularly useful in certain situations. So I could imagine a strange situation where evolution is conscious for a period, then it becomes something else, which is much more useful for the environment in which those brains and beings exist.
Vorrei fare prima un'osservazione anche e poi domanda. Il moderatore diceva che attraverso la luce è stata possibile decriptare la natura delle stelle. La stessa luce è interessantissima perché è il padrone dell'universo in senso di massima espandibilità come velocità. Esistono diverse spettrometrie, esiste anche spettrometria linguistica, dove attraverso le lettere, radici, si può trovare informazioni incredibili, addirittura di natura risposte cosmologiche quasi totali o fondamentali. Spettrometria numerica, basta 2 numeri fragmentali e riusciamo
può fare una domanda per cortesia?
Vabbè.
Cioè, se ha una domanda specifica, perché veramente mi hanno già fatto segno che dobbiamo finire magari...
Domanda è questa. E energia eguale massa or c al quadrato. Energia è sempre la stessa, massa è sempre la stessa, energia varia, ma velocità va all'infinito. Risposta che ha chiesto la persona, risposta alla coscienza, che se la materia è infinita, energia è infinita, conoscenza o informazione infinitamente infinita, e lo comprende. Esisterebbero 24 velocità della luce, non mc quadrato.
Ok, va bene. Io direi che se non c'è, perché mi hanno fatto segno che dobbiamo finire qui, quindi non è una domanda questa, sta facendo una lezione, scusi. Non è una domanda questa.
let me say something about the energy of the universe, which may be interesting. It was just remarked almost that it might be infinite. One of the strange discoveries in modern cosmology has been that we believe the energy of the universe is zero. And so if you imagined making a universe out of nothing, once upon a time people worried, how could you do that? Where would the energy come from? But the total energy of the universe seems to be zero. You would not violate the conservation of energy by bringing a universe into being. You might violate other things. How does this happen? It happens because if you take all the particles of matter and radiation in the universe and you add up their energies, you get an enormous positive score. But because gravity exists, there is a force of attraction between all these masses. And this is a so-called potential energy. It is negative. So if you let the particles go, they will attract and produce positive energy of motion. So if you add up all those energies of attraction between the masses, you get an enormous negative score. Einstein's general theory of relativity demands that one of its equations tells you that the big positive score plus the big negative score always has to be zero. So the total energy of the universe is zero. And it doesn't matter whether that's a universe that's going to expand forever or one that might one day turn around to a big crunch. So the issue of energy in the universe is a rather strange and unexpected one. That the universe is not like other things. It has a zero total energy, even though it sort of has an obvious substance to us.
Ok, dobbiamo finire qui, quindi ringraziamo ancora una volta John Barrow, Caleb Scharf, e grazie a voi, grazie.